In module 1, we have given some basic definition. In this module 2, we will start with linear autonomous homogeneous system of differential equations. We will look into the solution when the eigenvalues are real and distinct, and also we will look into the solutions when the eigenvalues are complex. We consider the first order linear homogeneous differential equation of the form dx dt is equal to Ax, where x is an n component vector x1, x2 dot dot xn, and A is a constant matrix because it is an autonomous system given by A11, A12 dot dot A1n, A21, A22 dot dot A2n, and AN1, AN2 dot dot ANn given by equation number 1. As we know that the space of solutions of 1 forms a vector space of dimension n. So, let us find a basis of the solution space, and for that we need to have n linearly independent solutions x1, x2 dot dot xn. Consider the scalar differential equation x dash, which is dx dt equal to Ax, and we can easily solve this differential equation just by separating the variables, where you write dx divided by x is equal to A dt, and if you integrate that, you will get the solution of the form xt is equal to some c times e to the power at, where c is an arbitrary constant. Now, taking this motivation from the scalar case, we may try the exponential solution xt is equal to e to the power lambda t times v, where lambda is a scalar constant and v is a constant vector as the solution of 1. Now, if xt is equal to e to the power lambda t into v is a solution of the system 1, then it is going to satisfy the differential equation, and hence we will get ddt of e to the power lambda t into v is equal to lambda e to the power lambda t times v, and a e to the power lambda t v is equal to e to the power lambda t a v. Hence, e to the power lambda t v is also a solution of 1 if and only if lambda e to the power lambda t times v is equal to e to the power lambda t into a v. Since e to the power lambda t is not equal to 0 for any lambda, so we divide both sides by e to the power lambda t, and we will get a v is equal to lambda v, which shows that lambda v is an eigenpair of the matrix A, where lambda is called the eigenvalue of the matrix A and v is the corresponding eigenvector. And hence, we define a non-zero vector v which satisfies equation 2 is called an eigenvector of A with eigenvalue lambda, and the pair lambda v is called an eigenpair of the matrix A. Thus, xt is equal to e to the power lambda t into v is a solution of 1 if and only if lambda v is an eigenpair of the matrix A. Thus, for each eigenvector v j of the matrix A with eigenvalue lambda j, we have a solution x j t is equal to e to the power lambda j t into v j of 1. To find n linearly independent solutions, we need to have n linearly independent vectors V1, V2 dot dot Vn with eigenvalues lambda 1, lambda 2 dot dot lambda n need not be distinct respectively, then x j is equal to e to the power lambda j t into V j, j equal to 1, 2 dot dot n are n linearly independent solutions of 1. Now, linear independentness of the solutions are guaranteed from theorem 1.4 discussed in the previous module, and the fact that x j 0 is equal to V j, j equal to 1, 2 dot dot n are n linearly independent vectors. In this case, the general solution x t of 1 is of the form x t is equal to C 1 e to the power lambda 1 t V 1 plus C 2 e to the power lambda 2 t V 2 plus dot dot plus C n e to the power lambda n t V n, where C i's I equal to 1, 2 dot dot n are n constants. Every solution of the system 1 can be written in the form of equation 3. So, our task of finding n linearly independent solutions of 1 is now reduced to find n linearly independent eigenvectors of the coefficient matrix capital A. In this regard, we have the following theorem, which says that if we have n distinct eigenvalues, then our job is done. So, the theorem states any k eigenvectors v 1, v 2 dot dot v k of A with distinct eigenvalues lambda 1, lambda 2 dot dot lambda k respectively are linearly independent. To prove this, we assume let lambda I and V I, where I equal to 1, 2, are two eigenpairs of the matrix A such that lambda 1 is not equal to lambda 2. And since lambda 1 and lambda 2 are the eigenvalues of the matrix A, we can write A V 1 is equal to lambda 1 V 1 and A V 2 is equal to lambda 2 V 2. Now, you can define your eigenvalue if and in another manner. If you look into this equation 4, you can take A as an operator which is acting on this vector V 1, and it gives you a scalar multiple of V 1, where V 1 is non-zero. So, any operator which acts on a vector and gives you a scalar multiple of that vector, then this lambda 1 is called the eigenvalue of the matrix A, and V 1 is the corresponding eigenvector. So, as discussed before, since lambda 1 and lambda 2 are distinct, we will get equation 4 and equation 5. Let C 1 V 1 plus C 2 V 2 is equal to 0, given by equation 6, where C 1 and C 2 are two arbitrary constants. Operating A on both sides of 6 and utilizing 4 and 5, we will have C 1 lambda 1 V 1 plus C 2 lambda 2 V 2 is equal to 0. So, what you are doing here is you are multiplying to the left hand side of 6 with A, and if you do that, you will get capital A C 1 V 1 plus capital A C 2 V 2 is equal to 0 matrix, and then C 1 is a constant, it will come out and you will get C 1 A 1 V 1 plus C 2 A 2 V 2 is equal to 0. Now, since A V 1 is equal to lambda 1 V 1 and A V 2 is equal to lambda 2 V 2, we will get C 1 lambda 1 V 1 plus C2 lambda 2 V2 equal to 0, given by equation 7. Now, we multiply equation 6 by lambda 1 and subtracting from 7, we will get lambda 2 minus lambda 1 into C2 V2 is equal to 0. Now, since lambda 1 is not equal to lambda 2 and V2 is a non-zero vector, the last equation implies that C2 is equal to 0. Using this value of C2 and the fact that C1 is also a non-zero vector, we will conclude that C1 is also 0, and hence both the vectors V1 and V2 are linearly independent vectors. We now look into the example where you have to find the solution of the equation x dot, which is dx dt, is equal to Ax, where A is the matrix 1 minus 1 4, 3 2 minus 1 and 2 1 minus 1. The very first thing you do is to find the characteristic equation of the matrix, which is defined by determinant of A minus lambda I is equal to 0, where I is the unit matrix 1 0 0, 0 1 0 and 0 0 1. And if you do that, you will get the determinant 1 minus lambda minus 1 4, 3 2 minus lambda minus 1, 2 1 minus 1 minus lambda is equal to 0. And if you expand that determinant and you simplify, you will get it in the form 1 minus lambda, lambda minus 3, lambda plus 2 equal to 0. And this characteristic equation actually gives your eigenvalues, and the eigenvalues in this case are 1, 3 and minus 2, and all are distinct. We will now calculate the eigenvectors corresponding to each of these eigenvalues, lambda 1 equal to 1, lambda 2 equal to 3 and lambda 3 equal to minus 2. So, what you do is you substitute lambda 1 is equal to 1 and you have to solve the equation determinant of A minus lambda I, where lambda is equal to 1 equal to 0. And if you do that, you will get this matrix equation 1 minus 1 4, 3 1 minus 1 and 2 1 minus 2 multiplied by u1 u2 u3 is equal to the 0 matrix. If you write this explicitly, you will get it in the form of these three equations, which is 0 dot u1 minus u2 plus 4 u3 equal to 0, 3 u1 plus u2 minus u3 equal to 0, 2 u1 plus u2 minus 2 u3 is equal to 0. Now, you have to solve these equations for u1, u2, u3 and for non-zero values of u1, u2, u3. And if you do that, you will get one of the solution to be minus 1, 4, 1. Please note this equation has infinite number of solution. So, the conclusion is for a distinct eigenvalue you may get different eigenvectors. So, once we work with one such solution and that solution we take as minus 1, 4, 1. So, this is your u1, this is your u2 and this is your u3. If you substitute these values in this equation, you will see that they are satisfying this whole system of equation, and hence we can conclude that u equal to minus 1, 4, 1 is a solution of this system of equation, and hence it is our required eigenvector corresponding to the value lambda 1 equal to 1. And hence we say x1 t is equal to c1 e to the power t minus 1, 4, 1 is the corresponding solution for any constant c1. In the similar manner, for lambda 2 equal to 3, we get the eigenvector in the form a minus 3 I into v is equal to 0. Again we will get 3 equations from if you multiply this and equate each of them to 0. Solving those 3 equations, we will get v equal to 1 to 1 as one of the solution, and we can conclude that the second linearly independent solution is given by x2t is equal to c2 e to the power 3t 1 to 1, where c2 is an arbitrary constant. In the similar line, for lambda 3 equal to minus 2, we will get an eigenvector of the form w is equal to minus 1 1 1, and hence our third linearly independent solution can be written as x3t is equal to c3 e to the power minus 2t minus 1 1 1 for any constant c3. Hence, every solution xt must be of the form xt is equal to c1 e to the power t minus 1 4 1 plus c2 e to the power 3t 1 2 1 plus c3 e to the power minus 2t minus 1 1 1, and which can be simplified and written in the form xt is equal to minus c1 e to the power t plus c2 e to the power 3t minus c3 e to the power minus 2t, 4 c1 e to the power t plus 2 c2 e to the power 3t plus c3 e to the power minus 2t, and c1 e to the power t plus c2 e to the power 3t plus c3 e to the power minus 2t. We have started this module with linear autonomous homogeneous system, where we have looked into the solution when the eigenvalues are real and distinct. We will now take the case where the eigenvalues are complex, and we will now look how to find the solution of this particular case. We now look into the system where the eigenvalues will be complex. So, let lambda equal to alpha plus I beta, where alpha and beta are real, be a complex eigenvalue of the matrix A, and let the corresponding eigenvector be v equal to v1 plus I v2. And hence, in place of the real solution, we have now the solution of the form xt is equal to e to the power lambda t into v as a complex valued solution of the differential equation x dot, which is dx dt is equal to ax, given by equation 8. We want to find two real valued solution from this complex valued solution. So, we have the following lemma, that let xt is equal to yt plus I zt be a complex valued solution of equation 8. Then both yt and zt are real valued solutions of 8. Now, the proof is as follows. If xt is equal to yt plus I zt be a complex valued solution of 8, then y dash t plus I z dash t is equal to a times yt plus I z t, which is equal to ay plus I a z t. On equating the real and the imaginary parts of equation 9, we have two real valued solution, yt is equal to real part of xt and zt is equal to imaginary part of xt. So, in place of two complex valued solution corresponding to the eigenvalues lambda and lambda bar, where lambda and lambda bar are complex conjugates, we can have two real valued solution yt and zt as obtained above. This will be explained better with the help of this example, where the initial value problem defined as dx dt, which is x dot, is equal to Ax, where A is the matrix 1 0 0 0 1 minus 1 0 1 1, and with the initial condition x0 is equal to 1 1 1 given by equation number 10. Now, from this matrix we first find the characteristic equation, which by definition is determinant of A minus lambda I is equal to 0. That is, in this matrix A, which is 1 0 0 0 1 minus 1 and 0 1 1, we write A minus lambda times I, where I is the unit matrix 1 0 0 0 1 0 0 0 1, and lambda is the eigenvalues which we need to find out. And if you put that determinant is equal to 0, you will come up with this equation 1 minus lambda into lambda square minus 2 lambda plus 2 equal to 0. And if you solve that, you will get lambda equal to 1 and lambda square minus 2 lambda plus 2 equal to 0. Solving this quadratic equation, you will get two more values of lambda as 1 plus I and 1 minus I, which are the complex conjugates. Now we have to calculate the corresponding eigenvectors for the values lambda 1 equal to 1 and lambda 2 and 3 equal to 1 plus minus I. Just like before, we calculate for lambda 1 equal to 1 the eigenvector, which is of the form v1, v2, v3. In this manner, we find A minus lambda I, and since lambda is 1, you have A minus I times V is equal to the null matrix, where V is your non-zero eigenvector. Substituting the values of A and I and simplifying, we will get the matrix equation as 0 0 0 0 0 minus 1 and 0 1 0 equal to 0, which gives 1 0 0 as one of the solution of the system of equations, and hence we conclude that a real valued solution of the differential equation 10 corresponding to lambda 1 equal to 1 is given by x1 t is equal to e to the power t 1 0 0. Now we look into the complex eigenvalues. For lambda equal to 1 plus I, we assume the eigenvector of the form u equal to u1 plus I u2. We substitute this in the matrix equation A minus lambda I equal to u equal to 0, where lambda is equal to 1 plus I. If you simplify this by substituting the value of A and I, which is the identity matrix 1 0 0 0 1 0 and 0 0 1, you will get the matrix equation minus I 0 0 0 minus I minus 1 and 0 1 minus I into u1 u2 u3 equal to the null matrix, where u1 u2 u3 is the required eigenvector corresponding to the eigenvalue 1 plus I. If we simplify this, we will get three equations of the form minus I into u1 plus 0 dot u2 plus 0 dot u3 equal to 0, 0 into u1 minus I into u2 minus u3 equal to 0, 0 into u1 plus u2 minus I u3 equal to 0. Now you have to choose the values of u1, u2, u3 in such a manner that you get a non-zero vector in the form capital U. In this case, we have taken that to be 0 I I. Please note there can be more than one solution of u1, u2 and u3, and you can choose any one of them as your corresponding eigenvector, which comes to the fact that for a unique eigenvalue there can be many eigenvectors. And hence, in this case our solution will be of the form x tilde t is equal to yt plus izt is equal to e to the power 1 plus I t into 0 I, which is a complex valued solution of equation 10. Now, calculation of the real and the imaginary part of x bar or x tilde, we have the following two linearly independent solutions of 10. Yt is equal to e to the power t into 0 minus sin t cos t, and zt is equal to e to the power t into 0 cos t sin t. And hence, we conclude that the general solution of equation 10 can be written in the form x general is equal to C1 e to the power t into 100 plus C2 e to the power t into 0 minus sin t cos t plus C3 e to the power t into 0 cos t sin t. And next, we use the initial condition x0 is equal to 1 1 1, and it can be shown that C1, C2 and C3 all have the values 1, and hence we conclude that the solution xt of the initial value problem 10 can be written as xt is equal to e to the power t multiplied by the matrix 1 cos t minus sin t into cos t plus sin t. Summing up, in this module we have taken the linear autonomous homogeneous system, where we have discussed the solutions where the eigenvalues are real and distinct, and also we have taken the case when the eigenvalues are complex. In our next module, we will discuss about the solution when the eigenvalues are real and equal. Thank you.